All right, so this week we're going to look at the complex um, branch impedances. So the last week we looked at the serial and the parallel RCL circuits. This time we're going to look at the combination. And we'll also talk about some of the power that is part of that and the power factors. All right, so just like in parallel DC circuits, the equivalent impedance of two impedances in parallel is equal to the product divided by their sum or the reciprocal formula. So that's the same as DC in our parallel circuits. So in this case, we would add up, so we would have Z1 here, which would be 5K plus J5K, or 5K at an angle of 0 degrees plus 5K at an angle of negative 90 degrees. And then this one would be Z2 would be 7K at an angle of 0 degrees plus 10K at an angle of negative 90 degrees plus 20K at an angle of positive 90 degrees. Then Z3 is going to equal 12K at an angle of 0 degrees plus 4K at an angle of 90 degrees. And that'll give you the Z1, Z2, and Z3. And then once we have Z1, we can calculate I1, which will equal Vs, right? Because remember, in parallel, the branch voltage is the same. So the voltage across here is the same as the voltage across here, which is equal to the voltage across here, which is all equal to Vs. No, where did my mouse go? All right. So once we get Z1, we can calculate I1 because the current is going to be the voltage divided by the impedance. Okay? And then once we get I1, I2, and I3, we can add those up to get I total. Right? So that's going to equal I1 plus I2 plus I3. Okay? And then ZT, Z total, is going to equal E divided by I total, where this is the Vs or Es. Okay? So let's take a look at how we would calculate this. So using the Sharp calculator in complex mode, Z1 is going to be the resistance plus the capacitive reactance. So that's going to be 5K at 0. So let me show you on the calculator. So here's the calculator. So again, we're going to put it in complex mode, and then we're going to make sure we're in the polar mode. So we'll go second 8. Now we're in polar mode. See how it says R and then theta? So then we're going to say it's going to be 5K, and then the angle, of course, is second here at 0 plus 5K at an angle of, and because that's capacitive reactance, it's negative 90. And we hit equal, we end up with 7.071K at an angle of negative 45. All right? And then if we do the same thing with the branch Z2 and Z3, so let's just do that, so we'll clear. So that's going to be 7K. So that's in that second branch, 7K. And you can put the angle on here. If it's 0, you can leave it off. But we're just going to add that plus 10K. And again, that is capacitive reactance, so that's going to be a negative 90 plus 20K, and that's at an angle of positive 90. And if we hit equal there, we get 12.206. Hold on, I must have added. Oh, I did 10K here instead of. Okay, that should be 7K angle 0 plus 10K plus 20K. Oh yeah, it's 12.2K at an angle of 55. So that's correct. 12.2K angle of 55. Then Z3 is going to be 12K. And because it's 0, I'm going to leave that off. Plus 4K. This one we do have to put the angle. And that's negative 90 degrees. Because that is inductive reactance. And that equals 12.65K at 18.4 degrees. All right? So that's how you can see the calculator to calculate those. All right, and then for the branch current, we're just going to divide the source voltage, 20 volts, by the impedance. So you can do those calculations on your calculator, and you'll see that you get I1, I2, and I3. And then we know that I total is just the sum of those branches. So that's going to be 2.8 plus 1.64 plus 1.54, and then you just add these, to add these, you can't just add 55 and negative 55 and negative. That doesn't work. You would have to convert that to rectangular, and then you can add them. Because remember, in polar, you can multiply and divide, and then in rectangular, you can add, subtract. But the calculator will just do that for you. And then once you get the total current, you can take the voltage of the source divided by the total current and its angle, which will be this 2.05, and it will become your your equivalent. And then you can test that by doing the parallel equivalent with the reciprocal equation, 1 over Z1 plus 1 over Z2 plus 1 over Z3, and that you get the same answer. All right, so now let's look at this one here. So let's just set up the formula. So let me draw this circuit. So I'm just going to say Vs equals 100 volts at 0 degrees, and then Z1 is going to equal 1.5K at an angle of 0 plus 3K at an angle of 90. Z2 is going to equal 4K at an angle of negative 90 plus 3K at an angle of 90. And then Z3 is going to equal 4K at an angle of 90 plus 3K at an angle of 0. Okay, so if we were to look at this formula, you can see the source voltage is still 100 volts, and then Z1 is just the sum here. So now if we come to our calculator, so let me switch this back. And so this first impedance here, right, which is going to be 1.5K at an angle of 0, so I'm going to just leave that off, plus 3K at an angle of 90, right, because that's an inductor. So Z1 is going to equal 3.35K at an angle of 63. And then Z2 is going to be 4K. Now there's no resistance in this one. So it's going to be 4K at an angle of negative 90, because that first one there is a capacitor, right? So let me show this section here. So it's 4K of a capacitive reactance and 3K of an inductive reactance. So I'm going to add those. And the inductor is, of course, positive 90. And that gives me 1K at negative 90. And that makes sense, right? Because I have 4K of in capacitive reactance and 3K of inductor reactance. And remember, the XL goes positive, right? It goes on our chart, it goes this direction. And then XC is at negative 90. It's basically saying this one is 4K, this one is 3K. What's left? And that's where you get the 1K at negative 90. And then this third branch is 4K at 90, right? Because it's an inductor, plus 3K at angle 0, and you can just leave that off, and you end up with 5K at 53.13. All right, and then we're asked, so there's Z1, Z2, and Z3. I1 is just going to equal Vs divided by Z1. I2 will be Vs divided by Z2, and I3 will be Vs divided by Z3. Then the total current is just the sum of I1 plus I2 plus I3. Now this theta, that is the angle that is for the resistance, the Z equivalent. So if you were to, so here, right, theta here for this one is this angle here for the Z equivalent. That's the angle for theta that we're looking for, right? Yeah. All right, so that's how you would solve that other one. All right, so now let's talk about power. Now, in instantaneous AC power, that's the product of the current and the voltage, right? Power equals I times E. And let me see here. Where is my... All right, so if we were to say the instantaneous AC power is the product of the current and voltage at each instant in time, so here is our voltage is the red line, our current is the green line, and then our power is the blue. So if we take the red times the green, that will give us the power, okay? And then the angle is 180 out of phase, right? So there's that. And then the average power, now so you see this is going between plus or minus. The average is just in the middle, okay? Now, the power average is just going to equal 0 volts on this one because it's going above positive and under positive for the current and the voltage. And you can see the average power is always going to be 0. All right? All right, so with this power, we're going to have a couple of different powers that we're going to deal with. The apparent power, and then the true power, and then we also have the reactive power. So notice the true power is from the resistance. The reactive power is from the reactance, which is either the capacitive reactance or the inductive reactance. And then the apparent power is from the impedance. All right? So it's important, and then here's our angle theta again. So the same right triangle that we've been talking about in just about everything is part of the power calculations. Now, power is calculated for resistance. It's the square of the current times the resistance, or the square of the voltage divided by the resistance, or it's the current times the voltage. All right? And of course, most of the time you're going to use RMS values, which are the values from meters. Remember, the oscilloscope defaults to your peak or peak-to-peak voltage. All right. So if we want to say what is the true power for a series RL circuit where the resistance is 5K, the capacitance or the inductive reactance is 5K, impedance is 7.07K at 45 degrees, and the source voltage is 20 volts, you could say IT equals Vs over Z. So that's the true power, or the total current is 2.82. Then total power or true power equals I squared R, which would be the current times the resistance, right? That's our resistance value, and that gets us 39.8 milliwatts. And then if we wanted to calculate the reactive power, instead of using resistance, we end up using the reactance. So in this case, it's I squared X, or Vx squared over X, or IVX. All right? So determine the reactive power for a series RL circuit. So this is the same circuit, right? 5K resistor, 5K of inductive reactance. The impedance is 7.07K at 45 degrees, and the source is 20 volts. So now we'll take the I squared X, and the current is the same, right? Remember, IT equals I1 plus I2 plus I3, or if it's series, it's all the same in one component. So you get the 2.82 milliamps squared times 5K, and that will give you 40 milliwatts of the VAR. And then apparent power is the power that the voltage source makes available to the whole circuit. And apparent power is the combination of the true power and the reactive power. It's not found by simply adding true power and reactive power, just as impedance is not found by the addition of resistance reactance. It has to be calculated. So the apparent power here is the total current squared times the impedance. So remember, the apparent power is the hypotenuse, and that is where the impedance is. So to calculate that, now we're going to take apparent power equals the total current times the source voltage, which would 2.82 times 20 volts, which gets us 56.4 millivolt amps. All right. Now, the power factor can be calculated as the true power over the apparent power. Or it's the power factor equals the IR squared times R, which is the true power, divided by the apparent power, which is the I total squared times the impedance. Okay? So in a series circuit, the power factor is just the resistance over the impedance. And in a parallel circuit, it's the current over the resistance divided by the current over the impedance current. Okay? And note that the IZ is going to equal IT in that one, because the total impedance and the total current are going to be similar or related. All right. Now, another way we can calculate the power factor is by taking the cosine of theta. Because remember, true power is the adjacent side and resistance power is the opposite side, and the cosine is the adjacent over the opposite. Or the apparent power is the hypotenuse. So there's some slides here that will explain some of that. All right. Now, the smaller the angle means the circuit is more resistive. Therefore, it's going to have more power dissipated in the form of heat, because remember our little triangle here. Let me go back here. Our resistive power, or true power, which is this side here, that's for our resistance. And that's the one where the power is dissipated in the form of heat. So the smaller this angle, the more true power we're going to have, which means there's going to be more heat dissipated. All right? So you can look at these and do these calculations. So if we combine some of these formulas to calculate the power factor, we end up solving pretty much all of our equations here. So this is just another way of determining the total power. It's just the I total times the voltage cosine 45 degrees, right? So we just take the calculations there. All right. Now, apparent power is the power the source can provide. So that's the total power, or the apparent power. True power is the power dissipated by heat because of the resistance. And the difference between the apparent power and the true power is wasted, because in reality only true power is consumed. Now, the ideal situation is to have a power factor of 1 or 100%, which makes it operate in unity. Now, the expression correcting the power factor refers to reducing the reactance. And the way a lot of manufacturers reduce that reactive power is to put a capacitor and an inductor in that startup circuit. So we'll talk about that in next week's lecture, where we're going to talk about inductance. All right, so that's it for now, and I'll talk to you later.